welcome back to another video. Now, in this video, we're going to be looking at projectile motion again, but in this video, we're going to be looking at particularly the concept of height in projectile motion. So I'm going to be teaching you how exactly to approach height problems whenever you encounter them in projectile motion. And again, I'm going to be looking at the different types of height you should expect to find when you're dealing with projectile motion problems. Okay, so let's get into it. Now, there are generally speaking two types of heights you should expect to find in your projectile motion problems. And here is the first type of height. Say you are given a cliff, and your projectile is launched from the top of the cliff, but it doesn't follow this trajectory. It doesn't follow this trajectory, which is more of half of this. If you look at this trajectory, where a projectile is launched from off a cliff, but horizontally, and then gravity does its work in making it trace this path, it's more like it's half of this trajectory, like half of the parabolic path you're used to. If it's a parabola, half of the path you're used to. But the first case we want to look at is not this kind of trajectory. We want to look at this type of trajectory, or the height associated with this type of trajectory, where our projectile has been launched from off the top of a cliff, but first goes up before it goes down. If you look at the previous trajectory, where the point was launched from off the cliff but with a horizontal velocity, the object which has been launched doesn't go up first, it simply goes down and horizontally at the same time. But in this case now, we've got an object that has been launched up first, so it goes up until it reaches this peak point, and then it begins to go down. But as it goes up and down, it has a horizontal velocity. That's why instead of just going up and down and comes back and hits this point, it goes through this entire path because of the horizontal component of the velocity it possesses during the motion. Now, the two types of heights we're going to be looking at today can be generally drawn from this trajectory. What are the two types of heights? The first type of height is generally considered or termed to be the maximum height reached by the trajectory during its motion. And it can be labeled thus: maximum height. This is generally speaking the maximum height reached by the projectile. Now let's label this as h naught. This is how I'm going to be labeling it. Now, because the projectile or the object is on top of a cliff, this cliff, and this is the ground, this cliff on its own has a height of its own. Now let's label this height as capital letter H. So this cliff over here is a height of capital letter H, and the projectile which has been launched from the top of a cliff moves through a height vertically of h naught. We'll pronounce this as h naught. Now, if we add these two heights, we get a height of h naught plus h, which is the height of the cliff, and we call this total height. Let's call it total height first. Total height, or in brackets. Now I'm going to put it in brackets, but this is the term you will usually come across. Rarely will they tell you or ask you about total height. They'll usually use this term I'm about to put in the brackets. So you can call this the total height or the peak height. Now you might be like, isn't peak height and maximum height generally the same thing? Yes, if you're looking at English, or if you're analyzing the English, saying peak height and saying maximum height is generally the same thing. But usually you have to confirm with your school curriculum what they mean by maximum height. For a lot of curriculums, maximum height in relation to the projectile simply means this height, the maximum height reached by the projectile, using this as the reference point, the point where it was launched from, using it as the reference point. That is what a lot of curriculums generally refer to as the maximum height. And then the peak height is usually measured with the ground below the top of the cliff as the reference point. So the peak height is measured from the ground, like this point over here as the reference point. But for the maximum height, you use this point or this point, generally any point at this level as the reference point. But for the peak height, use this as the reference level. But again, please confirm. Look at your curriculum, go and consult your physics teacher and ask them what or which term is associated with which length or which point. Whether they use the term peak height to refer to this length over here and use the term maximum height to refer to this length over here. But generally speaking, a lot of curriculums, when they say maximum height, they are referring to this portion, and when they say peak height, they are referring to this entire portion here. From this point up, down to this point. From this point, down to this point. So generally speaking, a lot of curriculums use this kind of nomenclature, if you will. But verify with your teachers, just to be sure. But in general, what I'm going to be teaching you here is still applicable despite the nomenclature you use wherever you are. What I'm teaching you here is still applicable. Just please make sure you understand the height you're being asked to find in the question. So let's get into the details and find exactly how we calculate the maximum height and how we calculate the peak height. Let's get into it. Now, before getting into the details of calculating the maximum height and the peak height, I want you to also keep this in mind. Now, if we have our normal trajectory, the trajectory a lot of people love, that seems to be very, very friendly or very, very simple, with this over here as your ground. And your projectile has been launched from this point with a velocity of, say, v at an angle theta here to the horizontal. With this situation, we do not have, okay, let me say this. In this situation, the maximum height and the peak height are just the same thing. So if you are asked to find the maximum height, now this is despite whatever curriculum you have. If you are asked to find the maximum height in this situation, where you have this normal curve, this simple looking curve, this can be called the maximum height or the peak height as well. In this situation, the two overlap. It's simply the same. So the methods in general I'm going to be teaching you of how to find the maximum height and the peak height, both of them apply to this situation and give the exact same answer if you apply them. Now, another scenario I want us to look at again before we get into the details is when we have a trajectory, say, of this kind. I talked about this trajectory. Say this is our cliff, and our trajectory is launched with a vertical velocity, not a velocity which is inclined or which is at an angle, but a vertical velocity, say, of v us in the presence of gravity, naturally our object will follow a path which looks roughly like this. Now, but like I mentioned earlier, this is simply the half of this kind of path, the path we've just talked about right now. This path is simply the half of this path, this entire path. It's like starting from this point and ending at this point. So once you know how to find the maximum height or the peak height in this situation, you already know how to find the maximum height or the peak height in this situation. It's exactly the same thing. Let's get into the details now. Okay, so I'm going to try to move really quickly now, so that we save time and the video doesn't become too long. So going back to our initial example where we have a cliff and an object that has been launched at an angle and first goes up and then goes down. Let's say the initial velocity, that is the launch velocity, is v, and the object has been launched at an angle theta. What I want to show you here is generally how to solve for the heights. Here we've got our height, h naught, and here we've got our height, capital letter H. Let me now switch colors. So how do we find our height h naught? Now, keep in mind, whenever we venture into calculations, and I'll keep repeating this, whenever we venture into calculations involving projectile motion, where we have to play around with the velocity, remember I said we do not take the velocity in its raw form. We break down the velocity into its constituent components and then use the velocity as suited in the equations of motion, as you see fit. So we want the height in this case. How do we calculate it? Which formula can we use to find the height? There are generally two formulas. V squared is equals to u squared plus 2as, and then we have s is equal to ut plus half at squared. Now, you must be careful. You might be asked to use them both. They won't say it explicitly, but implicitly it will be there. You'll find that you might have to use both of these formulas, or you might have to use this and the formula v is equals to u plus at, or this with the formula v is equals to u plus at. It just depends on the situation. Just look at the variables so you know exactly how you're supposed to tackle the problem. Now, in this case, we want to find the height h naught. But remember the initial velocity. Please watch the first two videos because I'm going to be moving a bit quickly, assuming that you already have the knowledge I imparted into you during the first two videos. Now, the initial vertical velocity in this case is what? The initial velocity is v sine theta. So we've got u is equal to v sine theta. And what is the final velocity when it reaches this point? The final velocity is equal to 0. We talked about this. The final velocity when our object reaches this point, we're talking about the vertical velocity, is 0. So when we come to say this case, let's first work with what? This case. Let's first work with this equation. Now, in this scenario, in this equation, we can use this equation to find this height. We substitute h naught for s. So we get something like this. H naught is equal to u what? This goes to ut, that is the initial velocity times time, plus half at squared. What is half at squared? It's the acceleration due to gravity times the square of the time. The acceleration due to gravity in this case, not in general. In this very case, that is the projectile motion problem we're dealing with. So keep in mind that I haven't changed anything on the right. I simply substituted h naught for s. Why did I do this? Because s is the displacement. in this case, h naught is our displacement, is the displacement we're looking for. That's why I substituted h naught for s. Now, what is our initial velocity? Our initial velocity, as we pointed out, is v sine theta. So we have, in this case, h is equals to v sine theta, and then we have the time. So it's v sine theta plus v sine theta times time plus half. What is the a? Say the a is, you're given an acceleration due to gravity of 9.81 or 10. Let's say 9.81. Now, in my case, like I mentioned in the previous videos, I prefer to use a negative when I'm dealing with the acceleration due to gravity. But you have to make sure that the moment you use a negative for the acceleration due to gravity, the velocity which is pointed up in this direction is positive, and any velocity pointed down is negative. But if you decide to use a positive value for the acceleration due to gravity, you're generally mixing or vice versa everything. This velocity where we're going up is then turned into a negative, and when we're going down it's turned into a positive. But generally speaking, I personally prefer to use a case where the acceleration due to gravity is negative, like so. I won't be inserting the units, just the values only. So it's 9.81. Then what is the time? We don't have it. So this is what we have. We have h naught is equals to v sine theta t plus half minus 9.81 t squared. Let me rub this off so that it doesn't confuse you. So we have this. How exactly then do we get our t? We get our t simply by what? By using this formula. Let me add it here. We use this formula. Remember, I told you that at time you might have to use this formula. We use our equation of motion, v is equals to u plus at. That's what we use to get our time. So in that scenario, we would have t is equal to v minus u plus a. You get this simply by making t the subject of the formula. So we've got our final velocity of what? 0. We've got our initial velocity of what? V sine theta. Remember, in some way or another, you'll be able to calculate this if this is what they want you to find. So we've got our final velocity of 0, and we've got our initial velocity of v sine theta, v being the magnitude of what? Of this velocity over here. And then we've got our acceleration, which is, generally speaking, or in this case, since we're looking at the projectile motion problem, is minus 9.81. So our acceleration is minus 9.81. Our final velocity is 0. Our initial velocity, which, because we took the minus, we put the minus on the acceleration due to gravity, will be positive. Our initial velocity of going up will be positive, such that we've got minus whatever value you have all over minus 9.81, and when you divide the two, you get a positive value for time. You shouldn't get a negative. If you get a negative value for time, you're probably messing around with the signs in the wrong way. So I'm simply showing you that it's easy to get the value for time. But which value for time exactly are you calculating in this case? You're calculating the value for time in this first portion of the motion. This portion of the motion, the portion where our object moves from the point A here up to the point B at the peak here. This portion of the motion. So the time you're calculating in this case is associated with this portion of the motion. Why? Because when we move from this point, when our object is launched from this point, it has an initial vertical velocity of v sine theta, and then when it reaches this point, it has a final velocity of 0. So the time you're going to get here is associated with the projectile moving from this point up to this point. But that's exactly what we need, because we need the height associated with this motion. We need the vertical height associated with this motion, which is what we're looking for. So once you get your time, all you have to do is simply substitute it into this expression. You do not have to memorize this expression, guys. Please remember, I do not urge you to memorize this. I urge you to derive it according to the situation. So you substitute in your value for t here, and you substitute your value for t here. You already have the acceleration due to gravity, and you already calculated this. So it's easy to get your what? Your value for the h naught. Your value for the height, the maximum height. This is how we calculate the value for the maximum height. And guys, this exact procedure, this exact derivation applies if your trajectory was looking like this, and you were asked to find the maximum height. If your trajectory wasn't something like this, but was something like this, and you were given the initial velocity, the angle, and they asked you to find the maximum height or the peak height, where you have a trajectory that looks more like this, you use the exact same procedure. Nothing has changed. You use exactly the same procedure. That is, if you want to use this formula, everything I described in this case applies if you are using this formula. You use exactly the same thing. You do not change a thing. In this case, you are looking at the part of the motion where our projectile has been left from this point, which again we can call A, up to this point where we can call B. You get the height in exactly the same manner we have just described for this funny looking situation over here, where our object moves from point A to B. This height here, which we're calling the maximum height here, is obtained in the same way you would obtain the maximum height in this case. But remember, I said in this case the maximum height and the peak height are the same. But in this case where you have this funny looking trajectory, the maximum height and the peak height might not be the same. Your curriculum might deem this as the maximum height and deem h plus h naught as the peak height. So I'm going to rub this and now show you how again we find this height using this formula. Now I've rubbed the equation s is equals to ut plus half at squared and left this equation here. This is an s, ladies and gentlemen. This is an s and represents the displacement of the object. Now we used the formula s is equal to ut plus half at squared when we wanted to calculate this height. Now I'm going to show you how to use this formula to do what? To calculate the exact same height h naught. So the first thing that we'll do here is make s the subject of a formula. How would we do that? We say v squared minus u squared is equal to 2as. How did we get this? We simply brought this from the other side, and then we divide by 2a. So we end up with something like this. S is equal to v squared minus u squared all over 2a. So we didn't do anything special here, guys. What we simply did in this case is simply make s the subject of the formula. Now, I want you to notice something. We've got the initial velocity, v sine theta. So what do? We simply substitute it in here where it's squared. We've got the we've got the final velocity. What do? We substitute it in here. Let me do this with you. So we've got s, the final velocity is 0. So we won't write anything, but we already have this. So we're going to end up with something like this. V sine theta squared, but you've already calculated this, so it won't be a problem. You've already calculated this. Now, and then we divide by 2a. Since a is the acceleration due to gravity, we will simply write 2g. But when you now substitute for the value Like I said, I prefer to use the negative. So in this case, if I were to substitute, I was going to write something like this. Minus 9.81. So this is it. If you're looking at this scenario, it's very, very easy to calculate what? The height h naught. So what you're going to do now, this is your height h naught. H naught is equal to minus, special attention to the minus, guys. If you do not use the minus, these two won't cancel out. Where is the minus coming from? It's coming from here. We substituted a 0 here, so we remain with the minus. This is going to be a positive. Why? Because you have already chose this to be a negative. If you choose this as a positive, this is going to be a negative. What do we get now? We get v sine theta. V sine theta squared all over minus 2 9.81. Now allow me to rub this so that you don't get confused. So this ends as your h naught, as your maximum height. When you decide to do what? When you decide to use this formula, v squared is equals to u squared plus 2as. In this equation of motion, you do not need to invoke this equation. You can simply use it as it is. Granted, you have all the variables given to you. Okay, so I've been showing you how to calculate the value of h naught, which I said is the maximum height. Now I want to show you how to calculate the peak height. What is the peak height? It's h naught plus h. H naught plus capital letter H is equal to the peak height. Now you might be like, okay, do we really have to calculate the peak height? Generally speaking, you have to calculate the peak height, but usually we are given the value for this height over here, which we have labeled capital letter H. We're usually given this height. So all you have to do is calculate the value for h naught using the methods that I've just shown you, and then you add it to the value of the height of the cliff, which you are usually given. By so doing, you get the peak height. But another way of finding the peak height without utilizing the value you are given here, maybe you're not giving this value, some way, somehow, let's say you're not giving this value. The way you find the peak height is by using the equation we have just looked at just now. S is equal to ut plus half at squared. The way you find the peak height, granted you're not given this, is by using the formula S is equal to half at. S is equal to ut plus half at squared. If you look at the trajectory starting from this point, at this point we've got a vertical velocity of 0. So you can use this vertical velocity as the initial velocity as of 0. So you now have a situation where ut, instead of using v sine theta, you're using the velocity at this point. You've got a case where u is equal to 0. Because this is equal to 0, we've got 0 over here. So we've got 0 plus half, still doesn't change. It's a g, acceleration due to gravity. Substitute minus 9.81 if you're comfortable with minus. But that is if the acceleration is 9.81. It might be 10. Look at your sheet. Look at the question sheet. And look at the value for the acceleration due to gravity they've given you. So we've got 0 plus half g t squared, which is simply half g t squared. So in this scenario now, the value for the time, let me write this here, the value for the time in this scenario, always Please bear this in mind. Do not try to grab this. Understand where it's coming from. The value of the time in this scenario is not associated with this entire motion. It's associated with the motion from this point B up to this point C. This point B up to this point C. So T is equals to the time from point B to the point C. And this is not the time of flight. Please bear this in mind, guys. The time associated with this part of the motion is not the time of flight. The time of flight is the time associated with the entire portion of the motion. Always be on the lookout of not using the wrong values. So now coming to this scenario, remember we have already touched on this scenario. I told you the way you find the maximum height in the previous scenario where we've got a funny looking trajectory where an object is launched from off a cliff but first goes up and then down. The way you find the H naught in that scenario, or the maximum height, is the exact same way you find the height in this scenario. There is nothing different. But the only thing I now want to add on in this situation is similar to what we've just looked at when we were dealing with the funny looking trajectory just now, where we had a B here and a C here. Now, remember in that situation, we said we can use the formula UT plus half AT squared. Now, the same thing applies in this situation. If you want to find the height using this part of the motion instead of this, you can find the height using this part of the motion. Using this exact formula, you can find the height using this part of the motion where you are moving from point A to point B. How do you do that? The initial velocity is v sine theta. You substitute your v sine theta, but remember guys, do not memorize v sine theta. It might be v cos theta depending on where the angle is situated. But in this case, because the angle is adjacent to the horizontal, we've got v sine theta for the initial velocity. Now, the time in this case, if you decide to use this first portion of the motion, the time which I'll label t1, and which is in this case, because of the symmetry, is equal to t2. But in this part of the motion, where you're using this section, where you're moving from point A to B, you use this time t1. Remember I said in this case where we've got this symmetrical parabola or hyperbola, whatever you choose to name it, in this case where we've got this symmetrical trajectory, t1 is always equal to t2. So in this situation, if you're looking at the first part of the motion, you have the initial velocity as v sine theta, the time as t1 associated with this part of the motion. How do you get the time? You can simply use the equation v is equals to u plus at, where the final velocity when it gets here is 0. The initial velocity, like we just mentioned, is v sine theta. The acceleration due to gravity is a, which is minus 9.81 if you wish. Then it all depends, but it all depends on the value of the acceleration due to gravity you're given. You might be given a value of 10. Please pay close attention to that. And then the t is what we're looking for. So you have the t once you use this formula, but you might be given the t. It all depends. Always pay attention to the information you're given. So you've got our initial velocity of this v sine theta, and then we've got our t, which we've just gotten from our formula, plus half a again. A is the acceleration due to gravity. You're given that. The t, we have just calculated it. So using this formula, using this equation of motion, and the time t1, looking at this part of the motion, we can get the height h0. But like I said, I want us to look at how we get the height h0 using this part of the motion. And again, there is nothing different from what we've just looked at. Because we're looking at this part of the motion from B to C, our initial velocity here pay attention, guys. Our initial velocity here, we now use this velocity and this. What we use as the final velocity at the top when we were using this portion of the motion is what we're now using as the initial velocity when we're looking at this portion of the motion. Now we already know that the vertical velocity at this point is 0. So that is now what we're using as the initial velocity. And remember, guys, we looked at this. There's nothing new here. We get a value of 0. It multiplies this vanishes, and you're left with half at squared. So we are left with, let me use a pink chalk. You're left with s is close to half at squared. But I'm using a g simply to remind you that that's an acceleration due to gravity. So you're left with s is close to half gt squared. This only happens if you're looking at this portion of the motion. That's where you use an initial of 0, an initial velocity of 0. If you're looking at the motion starting from this point up to this point. But now remember, guys, this t is associated with this. This t is associated with this t over here. But as I mentioned, in this particular scenario where we've got our nice looking trajectory, t2 will always be equal to t1. But just put it in mind, in this situation where you are calculating the height using this part of the motion, the t that we use is t2. That is the t associated with this side of the motion. But the formula remains the same. The only difference being that in this scenario we've got an initial velocity of 0, so we end up with something nice like this. But if you decide to use this part of the motion to calculate the height h0, this is h0. h0. If you use this side of the trajectory to calculate the height h0, always bear in mind that you do not have this formula. You simply use this y because this doesn't amount to 0 because you already have a value here, v sine theta, which when multiplied with your time gives you a certain value. It doesn't give you 0. So I hope that is clear. But again, why am I putting a major emphasis here on using this side of the trajectory, this part of the motion? The reason I'm doing so is because I want you to know this is the exact same, the way you calculate the height in this scenario, moving from this point up to this point, is exactly the same way you would calculate it. Granted, you were given a trajectory of this sort. A trajectory of this sort. I remember drawing this trajectory initially. If you are given a situation where you've got a cliff with a certain height, we do not know the height. If you are given a situation where you've got a certain cliff here and the object is launched with a vertical velocity, this only applies when the object is launched with a vertical velocity. The object is launched with a vertical velocity of v. In this situation, let's say you're asked to find the height h or h0. I just used the capital letter h, but it's still the same thing in this scenario. The letter h. You're asked to find the height of the cliff. You're either asked to find the height of the cliff. They say find the height of the cliff or the distance, the vertical distance or displacement through which the projected object has gone through. In this scenario, like I said, you're simply treating this as half of our initial trajectory. Remember, the thing has been launched with a horizontal velocity, meaning that it has got a 0 component of the velocity at this point. We've got a 0, we've got 0. If we try to find the vertical component of the velocity at this initial point where it has been launched with the horizontal velocity, we find that the velocity is 0. So in this situation, it's just like you're using half of the trajectory. That is the other half of the trajectory we just looked at. So we get an initial velocity of 0, and we use which type? we use the time associated with this portion of the motion where we're moving from B to C. So that's the time we use to substitute it here. And then we've got half A, that's the acceleration due to gravity, and then we use T. T simply being the same T as here, but we have to square it when we get to this point. So in this case, we no longer need to label it as T2. We can simply label it as T, or we can label it as T1, since this is an entirely different diagram altogether. So that is how you get the height if you are given this kind of a trajectory. And again, guys, you still use this formula if you want to find the time. You can still use this formula. How do you do it? Remember, in this case, the initial velocity is 0, so you put your 0 over here. Now, granted, you've calculated your final velocity, which is supposed to be here, the vertical velocity. You put it over here, and you put your acceleration due to gravity here with its appropriate sign, and then you find your t simply by making t the subject of the formula. So that is it, guys. That is how you find the heights, the maximum height, the peak height. Now again, in this situation, the maximum height and the peak height are simply the same thing. So in this situation where you've got the half trajectory, and then this situation where you've got the full trajectory, the height and the maximum height and the peak height are simply the same thing. But in that situation, when object is launched from off the cliff and the object first goes up and then goes down, we've got a certain type of height over here, and we've got another type of height below that is adding the heights, both the heights. So we've got the maximum height first, and then we've got the peak height, which is the addition of the maximum height plus the height of the cliff. So that is it, guys. That is all there is. Basically speaking, that is all there is to calculating heights. Always remember, we've got the maximum height, which usually is the same thing as the peak height, and then we've got the peak height. So we've got the maximum height and we've got the peak height, and in this situation what I'm simply saying is the maximum height h and the peak height is simply the same as h. These two are the exact same thing in this scenario. And if you had this trajectory over here, where you've got the full entire thing, the maximum height, this, and the peak height are exactly the same thing. It's simply this. But in that special case, where the object is launched from off the peak, off the top of the peak, and first goes up, after going up, and then comes down, this portion, this upper portion here, is what we call the maximum height. And this portion, the upper portion, the maximum height, plus the height of the cliff, is what we call the peak height, or the total height, if you will. But like I said, in this scenario, just verify with your teachers what in your curriculum is deemed the maximum height and what is deemed the peak height. Or if you ever use the term peak height at all, guys. Thank you, ladies and gentlemen. Thank you so much for your love, your support, for watching this video through up to the end, if you did. Thank you for that love, and I really mean it. Thank you, guys. Please leave a like, a comment, and subscribe if you enjoyed the video. See you in the next one, guys. Please do not miss the following videos. Enjoy. Oh, and guys, I almost forgot. It might happen that one is like, let's look at real problems where we are substituting values and all. I'll understand better if you start using real values. Like I mentioned in my previous videos, we are going to be looking at problem sets later, after I finish giving you a thorough understanding of the concept of projectile motion. First, understand what is happening. First, understand the details behind projectile motion. After we are done, then we'll be looking at problem sets associated with each topic we're looking at. And this topic, remember, we're simply looking at the height. That is what we were dealing with in this topic. Height, the concept of height. So we're going to be looking at associated problem sets in the future. Stay tuned so that you don't miss them. Thank you.